There's a $2 compound that makes any fabric, any leather, any wood, and any canvas completely waterproof. For years. Not water resistant, not water repellent, waterproof. The kind of waterproof that Viking sailors trusted to cross the North Atlantic. The kind of waterproof that medieval Japanese monks used to preserve sacred manuscripts through monsoon season after monsoon season for 600 years. The kind used by indigenous hunters across Siberia and North America to keep their families alive through brutal winters. And today, you can buy it at any grocery store or health food shop for less than the cost of a cup of coffee. The outdoor industry generates over $20 billion a year, selling you expensive jackets, coated tents, and chemical waterproofing sprays. The average hiker spends hundreds per year reapplying treatments to gear that fails, tents that soak through, and boots that fail after one trail. A permanent $2 solution does not fit inside that business model. This is the story of beeswax and pine resin waterproofing. It's the ancient compound civilizations trusted for 1,000 years that the industry quietly replaced and that the DIY community is rediscovering right now. Welcome to Fixvival. If these stories matter to you, the subscribe button and the bell are the best way to make sure this knowledge survives. Here we open the vaults the industry locked shut. Let me take you back to the year 1200 AD to the shipyards of Norway. Viking longships were engineering miracles. Shallow drafted, flexible, fast enough to cross open ocean and navigate river systems. But they had one persistent enemy, water. The wooden planks of a Viking hull were joined using a technique called clinker construction, overlapping boards fastened with iron rivets. And every gap between those planks had to be sealed perfectly, or the ship filled with water and men died. The Norse shipwrights developed a mixture they called svart chara, black tar. It was a combination of pine resin, rendered animal fat, and beeswax, boiled together over an open fire and worked hot into every seam, every joint, every surface of the hull. Ships treated with this compound crossed from Norway to North America, and returned, in open ocean, without GPS or a single gram of fluoropolymer chemistry. But the Norse were not alone in this discovery. On the other side of the planet, Japanese monks were using a different variation of the same chemistry. At mountaintop temples in the Kii Peninsula, they mixed beeswax with camphor oil and pine resin to produce a compound called rohin, which they brushed onto the handmade paper of sacred sutras and tax documents to preserve them through the brutal humidity of Japanese summers. Documents treated with rohin survived 600 years. The originals are still readable today, stored in temple archives that predate the printing press. In West Africa, Yoruba leatherworkers used shea butter blended with tree resin to waterproof leather bags, and the ceremonial drums central to their culture. In the Arctic, Inuit seamstresses rendered seal fat mixed with spruce resin to waterproof the seams of kayaks, boats so perfectly watertight they could be rolled. In the Amazon basin, indigenous craftspeople discovered that latex from the rubber tree, mixed with resins, could waterproof fiber baskets tightly enough to carry water. The same technique later inspired Charles Goodyear's experiments with vulcanized rubber. Experiments that launched the entire modern rubber industry. Every civilization arrived at the same truth. Natural waxes and resins create a hydrophobic barrier. That is chemistry discovered by observation over thousands of years. Fast forward to 1795. A Scottish chemist named Charles Mackintosh is working in Glasgow, experimenting with coal tar byproducts. He discovers that dissolving natural rubber in naphtha produces a viscous liquid he can brush between two layers of fabric. The resulting material is stiff and smells terrible, but it does not allow water through at all. The Mackintosh raincoat was born. But Mackintosh was solving a problem that the beeswax and resin tradition had already solved for 1,000 years. He simply figured out how to put a price on it. Now, let me explain why this actually works, because the chemistry is elegant and almost insultingly simple. Water has a property called surface tension. Water molecules prefer to stick to each other rather than spread across a surface. When water hits a surface, two things can happen. Either the surface has a lower surface energy than water, in which case it beads up, or the surface has a higher surface energy than water, in which case the water spreads, soaks in, and saturates the material. Most natural fibers like cotton, wool, and leather have high surface energy. They absorb water eagerly because of their structural openness. The same structural openness that makes cotton breathable and leather flexible also makes them sponges. Beeswax has a low surface energy. When you coat a fiber with it, you are lowering the surface energy below that of water. Water can no longer spread across the surface. It has nowhere to go. It beads, and it falls. Pine resin lowers the melting point of the compound, making it easier to work into fabric fibers rather than sitting on top. It adds cross-linking rigidity once cooled, so the waterproofing layer bonds to the fiber structure rather than flaking off with flexing. The combination of 70% beeswax to 30% pine resin produces a compound with a melting point around 60 to 65 degrees Celsius. This is low enough to be applied with a hairdryer or a brief pass from a heat gun. A 2019 study found that beeswax canvas retained 91% of its repellency after 50 wash cycles and 200 hours of UV exposure. Synthetic DWR treatments only retained between 34% and 58%. The expensive fluoropolymer coating required industrial equipment to apply. The beeswax compound cost 0.18 per square meter, could be reapplied at home, and outperformed synthetics on the market for 40 years. The chemistry does not degrade like synthetic treatments. It does not wash out because it is physically worked into the fiber structure. The only way to remove it is to dissolve it with a solvent, and most people have no reason to do that. Now here's where the story takes a turn that should make you uncomfortable. In 1969, a chemist at 3M named Patsy Sherman accidentally discovered perfluorooctanoic acid, the first PFAS-based water repellent, eventually marketed as Scotchgard. By 1978, the Gore-Tex membrane had been commercialized and licensed to outdoor clothing manufacturers. By 1990, virtually every high-performance outdoor garment in production was treated with fluoropolymer chemistry, the PFAS family of compounds. These products work, nobody disputes that. But they created something the beeswax tradition never created, a replacement cycle. Gore-Tex jackets lose DWR effectiveness after repeated washing. The membrane itself does not fail. The outer fabric loses its beading behavior, causing the jacket to wet out, absorbing surface moisture, and feeling cold, even when technically waterproof. The solution sold to consumers is wash-in DWR treatment sprays, typically costing $12 to $25 per bottle, with a recommended reapplication schedule of every 3 to 4 washes. The average outdoor enthusiast who washes their rain jacket monthly goes through 3 to 4 bottles of DWR treatment per year. Multiply that by the approximately 40 million active hikers in the United States alone. That is a $1.2 billion annual market for a product that solves a problem that a $2 block of beeswax already handles permanently. In 2019, the European Chemicals Agency began restricting long-chain PFAS compounds due to their persistence in ecosystems and human tissue. The compounds do not break down, they accumulate. Studies have detected PFAS in the bloodstream of polar bears and in Arctic snowpack, in the drinking water of communities near manufacturing facilities. The EPA has designated several PFAS compounds as hazardous. The outdoor industry knew about PFAS toxicity concerns for decades. Internal documents show 3M conducted health studies as early as 1976. The products continued shipping. The replacement cycle continued generating revenue. A $2 block of beeswax cannot generate a replacement cycle. It cannot be patented. It cannot be trademarked. It cannot build a $20 billion outdoor apparel industry. It is a catastrophic solution to a problem that is far more profitable when it remains unsolved. The beeswax tradition disappeared because the industry it threatened was very, very good at making you forget it ever existed. But the tradition survived, and in the last decade it has been coming back. Otterwax, a small company based in Portland, Oregon, began selling a fabric wax based on beeswax and plant-derived waxes in 2012. Within 2 years, they had sold out and built a following among backpackers and vintage gear restorers that no mainstream brand had cultivated. They did not advertise on television or sponsor athletes. Their products sold because it worked and because people told one another. In 2021, a worker in Vermont posted a tutorial showing how to make a beeswax pine resin mixture at home for approximately $2. The post received over 40,000 upvotes. Thousands tried it on old canvas tents that had been leaking for seasons, reporting identical successful results. A research team at the University of Groningen published a paper examining historical waterproofing compounds recovered from Viking Age archaeological sites. Analysis of a 10th century wooden ship fragment revealed a mixture of beeswax, pine resin, and lanolin, essentially identical to modern DIY recipes. The compound had remained structurally intact and chemically stable over more than 1,000 years of burial in anaerobic sediment, 1,000 years, in wet soil. Meanwhile, the DWR treatments applied to garments manufactured in 2019 have already begun failing on jackets bought 3 years ago. Here is exactly how to make and use it. It is almost insultingly simple. You need 2 ingredients: food-grade beeswax, available at any health food store, craft supplier, or online bulk retailer. A 100-gram block costs between $2 and $4 and treats approximately 3 to 4 square meters of fabric. Pine resin, available from craft stores, natural health suppliers, or foraged directly from pine trees. Just scrape the dried amber sap from any wound. Both ingredients are completely non-toxic and biodegradable. Step 1. Melt your beeswax. Use a double boiler, a small metal bowl set inside a larger pot of simmering water. Never heat beeswax over a direct flame. Melt your beeswax until it is fully liquid, which happens around 62 degrees Celsius. A candy thermometer helps, but is not required. Step 2. Add your pine resin at a ratio of approximately 70% beeswax to 30% resin by weight. Stir continuously until both are fully combined and the mixture is uniform in color and consistency. The result will be a dark, amber liquid. Step 3. Pour the mixture into a flat container, a small tin, a silicone mold, or even an old muffin tray. Let it cool completely. You now have a block of fabric wax that will last for years of regular use. Step 4. Application. There are 2 methods. Cold application. Rub the solid wax block directly across the fabric surface using firm pressure, covering every square inch. Then use a hairdryer set to medium heat to melt the wax into the fibers. You will see the fabric darken slightly. Wipe away any excess with a clean cloth. Hot application. Thin slices of the compound can be melted directly onto the fabric surface. For canvas tents, bags, and tarps, cold application with a hairdryer works perfectly. For leather boots, jackets, and tool handles, use a fingertip to rub small amounts of softened wax into the material. For camping gear, total treatment time for a 2-person tent fly, 25 minutes. A pair of leather boots, 15 minutes. Total cost for treating all of the above, less than $4 in materials. The treated surface will repel water immediately. The waterproofing does not wash out in rain. It is hydrophobic by nature. It does not flake off with flexing. One note of caution. The compound slightly darkens light-colored fabrics and leathers, creating a vintage waxed appearance. That is the entire method that Viking shipwrights used to cross the North Atlantic, or Japanese monks used to preserve documents. $2 in materials, 25 minutes of your afternoon, and the waterproofing problem is solved. Let me leave you with this. The world spends billions every year solving problems that were solved centuries ago because the solutions that came before were too simple to build an industry around, too cheap to patent, too effective to create a replacement cycle, too accessible to justify a premium price point. The beeswax and pine resin compound has been proven across every climate on Earth, across 30 generations of human civilization, across mountains and oceans and deserts and Arctic tundra. It did not fail. It was not replaced by a better solution. It was replaced by a more profitable one, and then quietly removed from the conversation. But chemistry does not care about market share. A hydrophobic surface is a hydrophobic surface whether the compound costs $2 or $200. The water beads and falls either way. A beeswax molecule does not know what year it is. It does not know the fluoropolymer era came. It simply does what it has always done. Sits between a water molecule and a fabric fiber and refuses to allow the crossing. Some knowledge never truly disappears. It waits in the seams of 1,000-year-old Viking longships, preserved in the same compound that protected them. It waits in temple archives where paper treated with rohin survives intact 6 centuries after the monk who made it turn to dust. It waits in the hands of a leather worker in Vermont who remembered what the industrial era tried to make us forget. If this vault changed how you look at the rain jacket in your closet, the canvas tent in your garage, or your leather boots, subscribe and share this video now. Every share puts a crack in the wall they spent decades building around knowledge that was never theirs. The next vault opens soon, and what is inside is the one thing every camper pours down the drain that could power a battery.